Welcome back, everybody, for another deep dive. This time, we're going to look at the origins of information theory.
It should be really interesting.
Yeah, it is. I've been looking at the listener-submitted sources, and wow.
It's a fascinating history.
Yeah, it is. It's a fascinating history, and there are so many twists and turns that I never would have imagined, and we're going to try to unpack all of that.
Yeah.
So I think the best place to start is with one of the sources that talks about 19th century American settlers and how they were using barbed wire fences to communicate.
Yeah, it's kind of a strange place to start, but
Yeah, barbed wire fences.
but it really illustrates like the need to communicate, right? It's a basic human need.
Yeah.
And these settlers, they strung up these barbed wire fences and then they would tap on them.
Wow.
And the vibrations would carry across long distances. And it wasn't Morse code or anything like that. It was just like
Wow.
maybe market updates or like, hey, there's a storm coming, or just
Oh.
basic information.
This is like a really early telegraph.
Yeah.
Just kind of hacked together.
Exactly. And it's all based on this idea of a network, which is essential for all communication. Information has to flow somehow. And this is like a very early basic example of creating a network.
Right. Okay. So we're starting with barbed wire fences.
Yeah.
But we're talking about the origins of information theory. So
Yeah.
how do we get from the barbed wire fence to, the digital age and everything else?
Well, the journey takes us to Bell Labs in the early 20th century. And there were two brilliant minds there, Harry Nyquist and Ralph Hartley.
Okay.
And they were doing really important work.
Bell Labs.
Yeah.
Okay. All right. So we went from barbed wire fences to Bell Labs. That's quite a jump.
It is.
So what were these guys working on?
Well, they were asking these fundamental questions about how to transmit signals over telephone lines. Like, if you think about it back then, sending voices over long distances was cutting edge.
Yeah.
Like, how do you make sure that the calls actually go through clearly? And, in doing that, they came across concepts that would completely revolutionize the way we understand information itself.
Okay.
So Nyquist, for instance, he made some groundbreaking discoveries about digitizing signals.
Digitizing, like turning them into ones and zeros.
That's exactly right.
Wow.
And this was way before computers.
As I know.
Like, we know them. So his work was really revolutionary. He figured out that you could take a continuous signal, like a sound wave, and you could sample it at regular intervals.
Right.
And then by measuring those samples and rounding them off, you could represent the signal as a series of discrete values.
It's almost like he was thinking about a digital format, but there wasn't even the technology to use it yet.
Exactly. It's mind-blowing.
Yeah.
And this insight really did lay the groundwork for the entire digital age.
Wow.
Everything we do with computers, smartphones, the internet, it all stems from that fundamental idea.
Okay. So Nyquist cracks the code on digitizing signals.
Yeah.
What about Hartley? What did he do?
Well, Hartley tackled a different angle. He was more theoretical. He was trying to define and quantify information itself. Up until that point, information was kind of this vague concept that we all intuitively understand, but nobody could really measure it or analyze it mathematically.
Right.
So he was trying to pin down what information is
Yeah.
at its very core.
Okay.
And Hartley had this incredible insight. He realized that information is fundamentally about making choices. Like, imagine you have a set of symbols, the letters of the alphabet, let's say.
Right.
Every time you choose a symbol, you're conveying information.
So it's not about what the word means, but the act of choosing the letters.
Precisely. It's the act of choosing. And
Yeah.
that constitutes information. And so he realized that information could be measured mathematically based on the number of choices involved.
Oh, wow. Okay, so that's really interesting. So Nyquist figures out how to turn continuous signals into digital ones, and Hartley develops a way to measure information itself. But how did this influence the development of information theory going forward?
Well, their ideas didn't really catch on right away. It was like planting seeds. They needed the right conditions to grow.
Yeah, okay, I get it. So they were sort of ahead of their time.
Yeah, exactly. And that's where Claude Shannon comes in. And he was this brilliant mind, fascinated by codes and puzzles, and he was working on his PhD thesis at MIT, and he was really grappling with this question of how to create a truly universal language of logic. So before we get to Shannon, though,
Okay.
I think it's important to understand the context of what was happening at Bell Labs.
Okay.
So we talked about Nyquist and Hartley,
Right.
but there was another Bell Lab scientist, John B. Johnson, and his work was also really crucial.
Another one. Okay, what was he working on?
Well, he was looking at distortion in electrical circuits. And
Distortion.
yeah, so he was studying these electrical circuits, and he kept noticing that there was always this inherent noise
Uh-huh.
that interfered with the signals.
So like static.
Yeah, exactly. Like if you're playing a game of telephone
Right, right.
and it gets all garbled, it was like that. But at the time, this was a big mystery. And Johnson realized that this noise wasn't because of any problem with the circuits themselves. It was something fundamental
Oh, wow.
to the electrical components.
So it was like a limit to how clear a signal could be.
Yeah, exactly. It was like this unavoidable randomness that was creeping in.
Wow.
And that's where Nyquist's work on digitizing signals becomes important again. You remember he figured out you could sample a continuous signal?
Yeah, at intervals,
Yeah.
and then digitize it.
Exactly. Well, Nyquist also came up with some mathematical formulas
Okay.
to describe this noise that Johnson was seeing.
Hmm.
And he understood that noise was always going to be a factor,
Right.
but his work helped to figure out how to minimize that impact.
Okay.
So, it's like laying the groundwork for sending clear signals even when there's static in the background.
Yeah, that makes sense.
All right, now while all this was happening with Nyquist,
Uh,
Hartley was working on a more conceptual question.
right, like what even is information?
Exactly, and how do you even begin to measure something like that?
Right, yeah.
It seems so intangible.
Yeah.
So Hartley realized that you have to step back from the meaning of a message and look at information just in terms of choices.
Choices?
Yeah, he saw information as a series of selections from a set of possibilities.
Like if you're sending a message in Morse code,
Yes.
it's not about the words themselves, but the dots and dashes.
Exactly. The dots and dashes represent letters, but it's the choice you make that
Right.
makes it information. And so he was able to come up with a formula
Wow.
to relate the amount of information to the number of choices available.
So he was quantifying it.
Yeah, he was basically giving it a mathematical framework.
Interesting.
Now, here's the thing. Both Nyquist and Hartley,
Yeah.
they were both at Bell Labs,
Right.
but their ideas, they didn't really take off immediately.
Oh, really?
It took a while for people to really grasp how significant they were.
Sort of like Van Gogh. Nobody appreciated his paintings until after he was dead.
Exactly. It's like that. And so this brings us to Claude Shannon.
Okay.
So he was a brilliant guy
Right.
working on his PhD at MIT.
Uh-huh.
And he was really grappling with this question that had plagued mathematicians for centuries.
Okay.
How do you create a truly universal language of logic?
Wow.
So mathematicians had always been searching for a way to formalize logic
Okay.
so that they could eliminate all the ambiguities of natural language.
Right. So like remove all the gray areas.
Yeah.
Make it completely black and white.
Exactly. So every statement could be definitively proven or disproven,
Yeah.
but there was a problem. Kurt Gödel and his incompleteness theorem.
Oh, yeah. I've heard of that, but it's a little fuzzy.
Yeah. So Gödel, he basically showed that any system of logic, if it was complex enough, there would always be statements that were true but couldn't be proven.
Within that system.
Yes. So even in this perfect world of logic,
Right.
there were limits to what you could know for sure.
So it was sort of unsettling.
It was very unsettling.
Yeah.
And it really shook the foundations of mathematics.
Wow. Okay. So how does Shannon tie into all of this?
So Shannon stumbled upon the work of Nyquist and Hartley,
Okay.
and he had this incredible realization.
Okay.
He realized that you could combine their insights about signals and information with Boolean logic.
Oh, wow. Remind me what Boolean logic is.
Right, so Boolean logic, it's the system that uses just two values,
Okay.
true and false.
Right.
And you can combine these values using things like AND, OR, and NOT to make more complex expressions. It's like the basis of all digital circuits and computer programming.
Right. Okay. It's coming back to me now.
So Shannon saw a way to use Boolean logic to represent and manipulate information in this really precise and efficient way. And this realization led to one of the biggest breakthroughs.
Really?
Yeah, in the history of technology.
Wow.
But to understand why this was such a big deal, we need to talk about another brilliant mind. Alan Turing.
Alan Turing.
That's him. But Turing was so much more than just a code breaker.
Right.
He's really the father of theoretical computer science.
Okay.
And his work is really important for this whole story of information theory.
But how does his work, which I always thought was about computers, how does that connect to all of this? Signals and noise and all of that.
Well, that's the question that will lead us to the heart of the digital revolution.
Right. So last time we ended on a cliffhanger.
Yeah, we did.
Alan Turing, father of theoretical computer science. How does he fit into all of this?
So Turing, he was also fascinated by systems, just like Shannon. How do you describe and manipulate information using a formal system
Right.
But Turing was coming at it from a slightly different perspective. He was thinking about computation.
Okay.
Like, what makes something computable?
I mean, I think of computation as math problems, but it sounds like he was thinking of something bigger.
Yeah, he was really thinking about any kind of process that can be broken down into steps, and then could those steps be done by a machine? So he imagined this theoretical machine.
Okay.
It's what we now call a Turing machine.
Okay.
And this machine could read symbols from a tape,
Okay.
manipulate those symbols according to rules,
Okay.
and then write the results back onto the tape.
So like a really, really early version of a computer program,
Exactly.
with the tape being the memory
Yeah,
and the actions of the machine are like the code.
you got it. And the remarkable thing is,
Yeah.
Turing showed that this simple machine could theoretically do any computation.
Wow, really?
Yeah, as long as you could describe it with an algorithm.
So anything you could solve by following instructions.
Exactly. And that's basically the concept of a universal computer. A machine that can do any task if you can break it down into those logical steps.
So this is where he connects to Shannon's work.
Yeah, because they were both thinking about how to represent information and then manipulate it.
Right.
But Turing focused on the computation part. And Shannon was looking at information itself.
So two sides of the same coin.
Exactly. And they both came to this same conclusion. Binary code was the key.
Oh, wow. Because computers use ones and zeros to represent everything.
Right. But it's interesting how they both arrived at that idea independently.
Yeah.
It goes back to Hartley's idea.
Okay.
Information as choices.
Right.
You have to reduce uncertainty.
Yeah, the more choices, the more information you need.
Exactly. And binary code, it's just two symbols, 0 and 1.
Right.
And that's the simplest way to represent those choices. Like a series of yes or no questions.
So you can take anything complicated and break it down into simpler choices.
Exactly. And Turing and Shannon both saw how powerful this was.
Oh.
Turing used it for his Turing machine, and Shannon showed it could encode and transmit information.
Wow. So it's all connected.
Yeah, it really is. It's amazing.
And that leads to the digital revolution.
That's right. Everything we do with computers today.
Right.
The internet, videos, email, and all of that relies on these ideas using binary code.
It's kind of mind-blowing that all of this came from such abstract thinking.
It is. It really is.
From those very basic questions.
Yeah.
About information and computation.
And it all goes back to those settlers with their barbed wire fences.
Right. They just wanted to communicate.
It's a basic human need. And even though the tools have changed so much, that need is still the same.
Wow. Okay, so this has been an amazing deep dive. Thank you so much. I feel like I have a much better understanding of how we got to where we are today.
Absolutely.
And it all started with barbed wire fences.
Who knew? And for everyone listening, hopefully this has given you some things to think about. Like, if information really is just a series of choices, what does that tell us about knowledge? And how does the way we share information change the way we understand the world? There's a lot to unpack there. Thanks for joining us.